Hello, this is my Applied Electromagnetics course project, Cavity Resonator. The purpose of this project is to design and build a cavity resonator at a chosen frequency between 500 MHz and 1.5 GHz. A cavity resonator is a hollow closed conductor which stores electromagnetic energy. When the cavity is excited at one of its resonant frequencies, the oppositely moving waves form standing waves. I chose my desired resonant frequency to be 1.25 GHz. This frequency should work at EEE352 mode, which should also be the dominant mode for the cavity resonator. This means that there should be no lower frequency, resonant frequency for this cavity resonator. And the diagram on the left shows the dimensions of the cavity resonator as A, B, and D, and the formula on the right is used to calculate the cavity resonator resonance frequency. So I calculated using this formula my dimensions A, B, and D, and they should be 15 centimeters, 10 centimeters, and 20 centimeters respectively, in order to obtain resonance at 1.25 GHz at the dominant mode TE101. And also we need two monopole antennas, one to excite the cavity resonator with the given frequency, and the second to measure the output that there is resonance indeed at that frequency. And the monopole antennas should both be lambda/4 in length, which is 6 centimeters for 1.25 GHz. The input antenna should be placed where the magnitude of the electric field is expected to be maximum, and the output antenna can be placed anywhere in which electric field is non-zero, but the output should be expected in that certain way based on the location. And the y is equal to 0 phase is shown in the first diagram. And I labeled the first and second antenna's locations. The first antenna is the input antenna, and the second antenna is the output antenna. Like I said, the first antenna should be placed where electric field should be maximum. So since there's a standing wave inside the cavity resonator, and at the dominant mode, the standing wave is only half a wavelength. I showed it on the second diagram at the bottom. Z is equal to 0 and Z is equal to D is where electric field magnitude are 0, and at Emax is at Z is equal to D/2. So the first antenna should be placed there. And the second antenna, like I said, can be placed anywhere, but I chose it to be at A/2 D/4, since I thought it was simple that way. So the expected output should be Emax over √2. So I built my cavity resonator. What I did is basically I had a insulator box, and I covered it with aluminum foil, which is a conductor. I covered it only with one layer, and I made sure that the sides were all smooth in order to make it like a real box, because not making it properly or with gaps in between, it might cause unwanted modes, which I don't want. And I put some copper tape on the sides to close the box completely. And I put the two antennas on the locations I described on the previous slide. Basically, I had a 6 centimeter long copper wire for each antenna, and I soldered it to the middle part of the port, as shown the square metal piece. And I soldered the ground plate of the port, which is the square part, to the cavity resonator using the copper tape, because you can't solder on aluminum, and it actually just burns. So I had to use copper tape for that, and it makes it more firm, because we don't want it to be moving and changing in direction inside the box. Then I connected the network analyzer to the port of the first antenna, and the graph shown here is basically used to see the resonance frequencies of the cavity resonator. It is seen that at 1.27 GHz and 269 GHz, it's minus 11.9 decibels, and the goal was to achieve something lower than minus 10 dB, and this is achieved in this case. This means that this is a resonance frequency of the cavity resonator, and as it is seen, there is no lower frequency in which this is lower than minus 10 dB. This shows that this is a dominant frequency for the cavity resonator, and so the goal is achieved in this case. And also, unfortunately, I can't show you the other resonant frequencies of this cavity resonator, because the network analyzer only shows frequencies between 500 MHz and 1.5 GHz, and the next lowest resonant frequency is 1.67 GHz and then 1.8 GHz, so I can't really show those. The input signal I gave to the first antenna, the input antenna is shown in this oscilloscope screenshot. It's basically 1.17 volts peak to peak. And the output signal is measured from the second antenna when this is given, when the first input is given from the first antenna. And the expected output is sine 45 times 1.17 because, like I described earlier, the output antenna is placed where the standing wave is at pi over 4. So sine pi over 4 is calculated, which is 1 over root 2. And the peak-to-peak voltage should be 0.83. But the real output, as shown in the oscilloscope screenshot, is actually 0.706 volt peak-to-peak. So this shows that there is some loss in the cavity resonator. And I think this is normal because I can't do the box perfectly. Of course, there are some gaps in between, maybe really small, maybe that I didn't recognize, or some cracks, open places. And these might always cause some loss and not perfect quality factor, and this might be the reason. But I think the results are as expected. I mean, I get to have resonance at the desired frequency, only with some slight loss. And I think the purpose of this experiment is achieved in this project. And I think it was successful. So thank you for listening.